incredibly useful for all of this, so they can lead to completely new foundations for artificial intelligence of more logical and geometric nature. And they can also play a key role in assisting the mathematical exploration, because you see, invariants in any situation provide kind of privileged points of view on reality.
Welcome back to Chelonia Podcast, a podcast about the use of scientific discoveries and of technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi. I'm a science journalist, and in today's episode of the second season, our guest is Olivia Caramello, Associate Professor at the University of Insubria in Como, Research Associate and Visiting Professor of the Université Paris-Saclay, and President of the Grothendieck Institute. Professor Caramello, it's a pleasure to meet you, and would you please briefly introduce yourself?
Thanks for the kind invitation to give this interview. I am an Italian mathematician. My main research interest is the theory of Grothendieck toposes and its applications throughout different areas of mathematics. In fact, since the times of my PhD studies, I have been developing a new theory called the theory of toposes as bridges, which allows one to establish new connections between different mathematical theories by using toposes as unifying tools, and more generally to investigate mathematical theories in a very dynamical way by means of a multiplicity of different points of view. So I carry out both theoretical work and also explore applications of toposes in different contexts.
Okay, Professor Caramello, you have been working for many years on the so-called toposes developing the theory of topos-theoretic bridges. These look like an intimidating mathematical subject, but however, as you say, the basic principle underlying this theory are not so difficult to understand. Could you please briefly explain them to us?
Yes, actually, the very basic idea is very simple, so I will try to explain it in non-technical terms. So if we want to relate different things with each other, we should do it by means of the invariants that they share. So what are invariants? Invariants are the essential aspects of things which in a sense define their nature at a fundamental level, despite the great diversity of their possible manifestations. So invariants, because of this, are not necessarily visible to the naked eye, because what we come into contact with are their concrete manifestations. But if we are able to identify an invariant from a given concrete situation, the idea is to use it as a bridge to connect that particular situation with any other situation in which the same invariant can manifest itself. So I can give an example. Suppose you want to translate a text between different languages. So what you have to do when you read the original text is to extract its meaning in particular, and to use this as a tool for connecting the original text with any other language in which the same meaning can be expressed. So you see, in this context, the notion of meaning plays the role of an invariant, which allows you to actually perform your translation. Because you extract this invariant and then you look at how this invariant manifests itself in the context of the other language. And it is by means of this that you create a bridge connecting the original text with the translated text. So in mathematics, what I do is conceptually very similar. So I use toposes as spaces on which fundamental mathematical invariants are naturally defined. And so, you see, I exploit the possibility of embodying an essence of a mathematical theory through a suitably chosen topos and some invariants defined on this topos. And then what we do is to look at how these invariants can express themselves in the context of another theory, which can be completely different, which can belong to even a different area of mathematics. And so in this way, we are able to establish often very deep and surprising connections between different mathematical contexts.
And Professor, in this context, what Alexander Grothendieck and the institute that bears his name has to do with all of these?
Well, actually, Alexander Grothendieck has been the inventor of this fundamental concept of topos. So, Grothendieck, as you know, has been a very, very great mathematician whose work has revolutionized many areas of mathematics. But he has also been a philosopher and actually a kind of universal thinker whose reflections have touched almost any domain of knowledge. So for him, mathematics should be developed in a very conceptual and systematic way. And one of the most important concepts that he introduced in his work is indeed this concept of topos, which has great mathematical significance, but also very strong philosophical and conceptual significance. So Grothendieck himself said that this concept of topos is the most broad of all the concepts that he introduced. He regarded that as extremely important. And so when I had to choose a name for the institute I wanted to create, it was very natural for me to choose to entitle it to Grothendieck, also as a sign of gratitude for all the contributions he brought to mathematics, which are incredibly deep, and also in order to justify a series of activities that I was also interested in promoting, activities aimed at a valorization of his cultural heritage at large. You see, as I said, Grothendieck has been really a universal thinker, so he has left us a huge number of manuscripts, unedited works, which touch different themes, psychology, ethics, sociology, physics, philosophy, etc. So all of these works need to be studied, deciphered, etc. And so one of the aims of our institute, besides promoting the development of topos theory and its application within mathematics, is to valorize Grothendieck's heritage at large. So it was very, very natural to give this name to the institute. And in fact, in our board of directors, we also have Grothendieck's daughter, Joanna, that represents like the family heritage and supports us in our project.
Referring to the theory of topos-theoretic bridges, you say that these methodologies are interdisciplinary in character, and even though they find their theoretical and most natural expression in mathematics, they can be applied outside in subjects such as physics, computer science, linguistics, and philosophy. Can you tell us more about possible future application on this theory in these fields?
Yes, actually, as I explained earlier, the role of invariance is essential in any field of knowledge. You see, every time you want to establish connections between different contexts, if you want to do it in a proper, deep way, you necessarily have to go through invariance. So, of course, this theory of topos-theoretic invariance in mathematics can be taken as an inspiration for the use of invariance in any scientific field. So if we think about physics, for instance, in physics you deal with different formalisms, different languages for describing theories that can seem very unrelated, even incompatible with each other. If you think about quantum mechanics on the one hand and relativity theory on the other, a major problem of contemporary physics is the incompatibility or possible compatibility between these theories, and nobody has been able to answer this question. So you see, these topos-theoretic tools could be useful, for instance, for shedding light about the possible conciliation of apparently incompatible formalisms such as these ones. Or more generally, in physics, fundamental theme is the study of dualities. And dualities, again, are kind of bridges because you describe by means of different languages the same mathematical content. And so, again, if you want to be able to investigate the dualities in a deep way and being able to transfer all the knowledge that is actually possible to transfer, you need, again, to take the point of view of invariance and toposes, because they are these spaces on which the fundamental invariants are naturally defined. They are bound to play a key role in connection with these investigations. Of course, there is much more, again, that can benefit from a topos-theoretic outlook. But these are kind of two main directions that are certainly important to pursue. Concerning other fields, so if we think about computer science, well, computer science and engineering, now a major theme of research is artificial intelligence, also automated theorem proving or automated theorem generation, so tools that can help the mathematician in his everyday work, that can assist the mathematician in suggesting new ideas, results, etc. So toposes can be incredibly useful for all of this, so they can lead to completely new foundations for artificial intelligence of more logical and geometric nature. And they can also play a key role in assisting the mathematical exploration, because you see, invariants in any situation provide kind of privileged points of view on reality. So if you let yourself being guided by invariance, you are naturally led to uncover unexpected connections, to multiply points of view on a given subject. And of course, all of this is an essential prelude for deep understanding and solutions also to concrete problems. So you can understand that toposes can play a key role in connection with automated theorem proving and generation. And so in particular, we have recently started a research project, at the Institute, precisely in this direction. And of course, there are many scholars all over the world that are starting to explore applications of toposes in connection with the design of new foundations for artificial intelligence. Concerning other fields of knowledge, well, I have already mentioned linguistics in my basic example, and from that you can already understand how these techniques can be helpful in all sorts of comparative studies or theory of translations, etc. And in philosophy, also they can be very relevant in connection with the investigation of ontology and phenomenology, because you see, in a sense, when you think in terms of bridges, you think in terms of a two-level articulation. So you have the level of unity, which is the level where invariants lie, and you have the level of diversity, which is the concrete level of the phenomenological level of the invariance manifestations. So you have a concrete mathematical incarnation of the duality between ontology and phenomenology. So, of course, this, I think, can be very useful for supporting philosophical reflection on these fundamental topics. And, of course, I have just mentioned very, very limited number of possible directions. There is, of course, much more, but at least I hope it conveys an idea of the impact that these methods can have at large.
Fantastic, Professor. But now, what are you working on, and what are your future projects?
Well, actually, I work simultaneously on different projects, both of theoretical nature, so consisting in like the further development of topos theory, like theoretically, and also in connection with applications, mostly within mathematics, but also beyond it. So I work alone and in collaboration with colleagues, both senior colleagues and students and young researchers. In particular, I intensely work with my PhD students and postdoctoral researchers, both at the University of Insubria and at the Grothendieck Institute, which I founded precisely with the aim of training a new generation of young researchers on these interdisciplinary techniques. As a supervisor, I actually like to give my students very ambitious projects that can open new paths in a classical mathematical subject, thanks to the enlightenment that can be provided by a topos-theoretic outlook. So on the theoretical side, one major theme that we are currently exploring by using both geometrical and logical tools is the theory of relative toposes. So what do we mean by relative toposes? Well, it's the possibility of developing the topos theory not only in relation to the standard set theoretic foundation, but with respect to alternative foundations embodied by arbitrary toposes. So you see, in this way, one is no longer bound to a single fixed foundation, but one can choose the universe with respect to which one works, depending on one's needs, and also change it continuously by using the so-called relativity techniques. So you see, the relativity method was pioneered by Grothendieck in the context of schemes in his functorial refoundation of algebraic geometry, and what we are presently doing is to develop the analog of these techniques for toposes. And all of this makes the theory much more powerful because toposes are much more flexible than schemes. They are also much more general. And so these relativity techniques can be applied essentially everywhere in mathematics. So another important subject that we are presently investigating is the possible unification between the theory of motifs and the theory of toposes. So more specifically, we are investigating the possibility of constructing motifs, which are a kind of universal objects conjectured by Grothendieck, by means of toposes. So this is also a project that is very important for me and which I am investigating in collaboration with Professor Laurent Lafort.
Impressive, Professor. But now we are at the end of this podcast and finally, like a sort of bridge, if you could go back or forward in time, what would you like to know or discover?
Well, so if I could back in time, of course, I would like to see the birth of topos theory And so in particular, I would like to meet Grothendieck and talk with him about toposes, express him all my enthusiasm for this wonderful theory. So unfortunately, all of this will remain a dream, but still sometimes I find myself pondering about that. Concerning the future, what I would like to see is the flourishing of applications of toposes that will certainly come in the forthcoming years. So I just cannot wait to see the deep impact that topos theory will have on the mathematics of the future. You see, toposes really teach you to think in a different way. You see, they allow you to revisit any kind of mathematical subject with new eyes. So we can really expect a kind of dramatic impact. So there are still, at the moment, some resistances in the mathematical community to take these techniques, these topos-theoretic techniques, as seriously as they would deserve. You see, already Grothendieck complained about the bad reception of toposes in the 80s. And today we are still far from an ideal situation concerning the recognition of this subject within mathematics at large. But I think that, with time, you see, time typically brings truth and justice. So I think that with time, the relevance of this subject will become clear for everybody. So I see a very, very bright future for topos theory and their applications.
Thank you so much, Professor Caramello, and thanks our listeners. If you have any questions about today's podcast, you can get in touch on Chelonia Twitter and feel free to subscribe chelonia.swiss website and be part of the community. In meantime, stay tuned for our next interview. Thank you again, Professor.
Thanks to you.